Berlin, December 14, 1900. A cold winter scene shows Max Planck, a reserved 42-year-old professor, presenting a dry, technical paper to the German Physical Society. The room is quiet, the atmosphere lacking drama, as the reluctant revolution begins unnoticed. Planck introduces a formula meant to solve a niche problem in thermal radiation. This moment reveals Planck's defining paradox, a conservative man seeking absolute, immutable laws. His entire quest for classical order led him, against his deepest convictions, to the most radical scientific discovery of the new age. He stands as a reluctant revolutionary, a figure steeped in tradition who would later wrestle fiercely with the strange, uncertain universe he had reluctantly brought forth through his intellectual offspring, quantum mechanics. His story is a testament to his own tragic aphorism: a new scientific truth triumphs only when its opponents die. In a profound twist of fate, Max Planck became the first and most esteemed opponent of his own quantum revolution. Max Carl Ernst Ludwig Planck was born on April 23, 1858, in Kiel, into a distinguished lineage of German intellectuals. His family tree was rooted in legal scholars and theologians, instilling in him a deep respect for established institutions and order. Baptized as Marx, he soon adopted the more common Max, reflecting his preference for clarity and conventionality. His early life was shaped by an environment where intellect and duty were highly revered family values. When Planck was 9, his family relocated to Munich, a city vibrant with culture and learning. This move exposed the young scholar to a broader intellectual and artistic environment that profoundly shaped his sensibilities. An early memory surfaced from the Second Schleswig War, the site of Prussian and Austrian troops marching through Kiel. This provided an early, formative glimpse of the powerful historical forces that would later dominate his life. Attending Munich's prestigious Maximilians Gymnasium, Planck demonstrated a formidable dual aptitude. His mind equally embraced the structured logic of mathematics and the profound harmony of musical composition. He was a gifted classical musician, adept at playing the piano and cello, and possessing the rare precision of perfect pitch. For a brief period, he seriously contemplated dedicating his life entirely to a career in music. His path toward theoretical physics was cemented by his mathematics teacher, Hermann Müller. Müller guided Planck toward visualizing the underlying mathematical elegance and harmony hidden within the physical laws of nature. Planck ultimately chose physics, driven by the conviction that pure reasoning offered humanity a unique insight into the absolute mechanism of the world. Music, however, remained his lifelong sanctuary and a source of profound connection. In 1874, at the age of 16, Planck enrolled at the University of Munich. He sought advice from Professor Philipp von Jolly, who famously warned him that physics was largely complete, leaving only insignificant gaps to fill. Unentört by this discouraging assessment, Planck began his rigorous studies. His conservative mindset found reassurance in the prevailing belief that die fundamentalen laws des Universums waren already largely understood und immutabel. Following established academic tradition, Planck spent a year in Berlin, 1877-1878, studying under titans like Hermann von Helmholtz and Gustav Kirchhoff, absorbing the high classical traditions of German science. However, Planck's deepest intellectual revelation came not from lectures, but from intense private study of the seminal works of Rudolf Clausius, a pioneer in the mechanical theory of heat. Through Clausius, Planck discovered his scientific obsession, the second law of thermodynamics. He viewed the irreversible increase of entropy not as a statistical trend, but as an absolute, universal law of nature. This unwavering belief in the absolute validity of the entropy law became the philosophical cornerstone of his entire scientific worldview, underpinning his search for deterministic truth in all phenomena. In July 1879, at the young age of 21, Planck received his doctorate from Munich. His dissertation rigorously explored the second fundamental theorem of heat, establishing his command of thermodynamics. He followed this with his habilitation thesis in 1880, qualifying him to teach at the university level. Despite the depth of his early work on entropy, the scientific community at large paid little attention. After 5 years laboring as an unsalaried lecturer in Munich, his career finally gained momentum. In 1885, he secured an appointment as an associate professor at the University of Kiel, his native city. In Kiel, he began building his personal life, marrying his childhood friend Marie Merck in 1887. This domestic life provided the stable foundation against which his later scientific and personal dramas would unfold. The birth of his first son, Karl, in 1888 marked the beginning of his family. He envisioned a life rooted in domestic order, intellectual pursuit, and adherence to conservative German academic values. Planck's appointment to the University of Berlin in 1889 marked his ascent to the absolute apex of the scientific world, replacing the revered Gustav Kirchhoff and moving to the heart of the German Empire. Promoted to full professor in 1892, Planck held the chair of theoretical physics, solidifying his position as the world's foremost authority on classical thermodynamics and shaping the next generation of physicists. His status was further confirmed in 1894 with his election as a full member of the esteemed Prussian Academy of Sciences, a signal that he had arrived among the absolute elite of German academia. In 1897, he published his authoritative treatise Vorlesungen über Thermodynamik, Lectures on Thermodynamics, firmly establishing his undisputed mastery and conservative grip on the classical physics establishment. Planck and Marie settled in the affluent Berlin suburb of Grunewald, raising their 4 children, Karl, the twins Emma and Grete, and Erwin. Their home epitomized order and intellectual prosperity. The Planck home became a renowned cultural nexus, famous for its regular musical soirees. Max would often play the piano or cello, fostering friendships with colleagues and hosting Berlin's academic and artistic luminaries. Beneath the triumph of classical physics, a serious technical puzzle was brewing: the behavior of a black body. This theoretical object, when heated, emits radiation whose spectrum depends only on temperature, not material. Planck was intensely drawn to this problem because it promised a universal law, independent of messy material specifics, the loftiest goal of his scientific quest for absolute truth. Experimental physicists at the PTR, Germany's Imperial Institute, were meticulously measuring the black body spectrum using sophisticated, high-tech ovens, generating data that defied existing theories. The prevailing classical theory, the Rayleigh-Jeans law, worked accurately for low-frequency radiation, infrared, but its predictions spiraled catastrophically out of control at high frequencies. The theory predicted that as frequency moved toward the ultraviolet, the emitted energy should skyrocket toward infinity, meaning even lukewarm objects should emit endless high-energy radiation. This failure was dubbed the ultraviolet catastrophe, a clear and nonsensical signal that the fundamental principles of classical physics were inherently and disastrously flawed, marking the looming crisis. Planck devoted himself entirely to solving this anomaly, starting in 1897, hoping to derive a perfect blackbody law solely from the bedrock of thermodynamics and electromagnetism. For years, he attempted to rigorously derive Wilhelm Wien's formula, which worked well at high frequencies, but he struggled to force the complex reality into a classical mold. In the autumn of 1900, conclusive new experimental data arrived from the PTR, proving that Wien's law failed decisively at the low-frequency end of the spectrum, leaving physics utterly stumped. On October 19, 1900, Planck presented an empirical solution to the German Physical Society. It was an educated guess, a clever mathematical interpolation that instantly matched all known experimental data. Though immediately successful, Planck found this formula, lacking a physical basis derived from first principles, intellectually intolerable. He felt compelled to find a rigorous explanation for his lucky intuition. He plunged into 2 months of what he later described as the most strenuous work of my life, desperately trying to impose a logical, classical meaning onto his empirically perfect equation. By December 14, 1900, Planck had his derivation, but it demanded a radical conceptual break that violated his deepest convictions, an action he mournfully termed an act of desperation. To make the statistics work, he first had to reluctantly embrace Ludwig Boltzmann's probabilistic methods, a statistical view of entropy he had spent his entire career fiercely rejecting. Second, and far more consequential, he was forced to assume that the microscopic oscillators within the radiating blackbody walls could not exchange energy continuously as classical physics mandated. Instead, Planck posited that energy could only be absorbed or emitted in discrete, indivisible packets, which he named energy elements or quanta, a horrifying discontinuity to his orderly mind. He formalized the relationship: the energy, E, of a quantum was directly proportional to the radiation's frequency, U. Linking them was a new fundamental constant, H, now known as Planck's constant. The revolutionary equation, E equals h nu, instantly solved the ultraviolet catastrophe. High-frequency quanta were so expensive that the object lacked the thermal energy to produce infinite amounts, causing the spectrum to drop. In a desperate effort to preserve the classical integrity of thermodynamics, Max Planck had inadvertently introduced the fundamental granularity of reality, laying the irreversible cornerstone of the quantum world. The immediate reaction to Planck's quantum hypothesis was surprisingly quiet. For years, the scientific community, including Planck himself, treated the quantum concept as a mere formal, calculating trick lacking deep physical meaning. Planck was deeply uncomfortable with the fundamental discontinuity he had introduced. He spent years in a futile effort trying to find a modified derivation that would eliminate the need for discrete quanta and restore classical continuity. He remained a revolutionary against his will, earnestly hoping that his own discovery would eventually prove to be a temporary, transitional fix rather than the new, permanent foundation of physical reality. The turning point arrived in 1905, Albert Einstein's miraculous year. The 26-year-old patent clerk published a paper on the photoelectric effect, taking Planck's quantum concept literally for the first time. The photoelectric effect, light knocking electrons off a metal, could not be explained by classical wave theory, which incorrectly tied the effect to brightness, intensity, rather than color, frequency. Einstein proposed that light itself was quantized, composed of discrete particles, later named photons, whose energy was exactly E equals h nu. A single high-energy blue photon could eject an electron, while many low-energy red photons could not. This work transformed Planck's quanta from a peculiar property of radiating matter into a fundamental physical property of light itself, giving tangible reality to what Planck intended as a mathematical abstraction. Despite his hesitation about the quantum, Planck possessed an extraordinary intellectual honesty, instantly recognizing genius in others, especially Einstein, whose 1905 papers he read as a journal editor. While many dismissed Einstein's relativity papers, Planck immediately grasped their profound significance. He used his immense influence to ensure publication and became special relativity's most powerful, established champion in Germany. It was Planck in 1906 who coined the term theory of relativity, Relativtheorie, publishing follow-up papers that solidified the theory's standing and provided crucial academic backing for the young, unknown physicist. Planck's dedication to Einstein culminated in 1914 when he successfully campaigned to bring the intellectual renegade to Berlin, securing him a prestigious research-only post at the Prussian Academy. The two men, the orderly Prussian academic and the bohemian iconoclast, forged a deep, enduring friendship, often united by their shared passion for musical duets at the Planck home. Their bond survived significant scientific disagreements. Planck was initially skeptical of general relativity, cautioning Einstein in 1913 that his effort would likely fail and no one would believe it even if he succeeded. Yet, when Arthur Eddington's 1919 eclipse observations confirmed general relativity, Planck converted fully, praising the theory as an intimate union between the beautiful, the true, and the real. Planck received formal recognition when he was awarded the Nobel Prize in Physics in 1918, received 1920, specifically for his discovery of the fundamental energy quanta, cementing his place in history. By the 1920s, Planck was the revered elder statesman, the embodiment of German scientific integrity and authority, presiding over a field that was rapidly moving beyond his personal comfort zone. A new generation, Bohr, Heisenberg, Pauli, developed the Copenhagen interpretation of quantum mechanics, built upon fundamental principles that Planck found intellectually appalling: uncertainty and probability. Planck, along with Einstein, firmly rejected this new framework. He could never abandon his lifelong belief in strict causality and absolute determinism, viewing probability as a reflection of human ignorance, not objective reality. He held out hope that Erwin Schrödinger's wave mechanics would eventually provide a deterministic classical picture that would render the unsettling probabilistic core of the quantum theory unnecessary. Planck, the man who had sought absolute deterministic laws his entire life, found himself the principal figurehead resisting the probabilistic, chance-based universe that his own initial discovery had unleashed. In 1930, at the age of 72, Planck assumed the presidency of the Kaiser Wilhelm Society, KWG, Germany's vast network of elite research institutes facing the daunting challenge of declining revenues amid global crisis. Unlike Einstein, who immediately renounced his citizenship, Planck made the fateful decision to stay, believing his patriotic duty was to remain and try to protect the infrastructure and integrity of German science from political interference. Planck argued pragmatically that expelling brilliant Jewish scientists would cripple Germany's future scientific capabilities, specifically pleading the case of the highly patriotic chemist Fritz Haber. His attempt failed, and the purge continued. Planck and the KWG leadership retreated into a strategy of inner emigration, attempting to maintain scientific standards in private while offering little public resistance to the expulsions. Planck resigned from the KWG presidency in 1937 and from the Prussian Academy in 1938 as a quiet protest against the increasing Nazification, Gleichschaltung, of academic life, But the moral compromise had been struck. The 87-year-old Planck, having already lost his first wife, his eldest son in WW1, and both twin daughters in childbirth, now faced the execution of his last surviving child from his first marriage. In a final, desperate, harrowing act, Planck penned a direct, personal plea to Hitler in October 1944, appealing to the Führer's supposed respect for his everlasting intellectual wealth of Germany in exchange for his son's life. The final year of the war brought physical destruction. An Allied air raid in February 1944 completely annihilated Planck's Berlin home, incinerating his entire library, notebooks, and a lifetime of invaluable scientific correspondence. Evacuated with his second wife, Marga, to Göttingen, Planck faced the war's end surrounded by rubble and overwhelming grief, his intellectual life's record reduced to ash. Despite his advanced age and profound loss, Planck answered a final call to duty, assuming the acting presidency of the shattered Kaiser Wilhelm Society after the suicide of its Nazi-aligned leader, Albert Einstein. His enduring international prestige was affirmed when the Royal Society invited him, the sole German scientist, to attend the 1946 Isaac Newton tercentenary celebrations, a powerful gesture of global reconciliation. The Kaiser Wilhelm Society, tainted by its wartime complicity, was dissolved by the Allied powers. However, the idea of elite fundamental research institutes was salvaged. The organization was refounded in the British occupation zone on September 11, 1946, under a new, untainted name, the Max Planck Society, Max Planck Gesellschaft. Planck was named honorary president, a poignant tribute to the man who had twice led its predecessor. Today, the Max Planck Society is Germany's premier research body, a living monument to his dedication. In his final years, Planck remained an unwavering determinist, firmly rejecting the probabilistic core of quantum mechanics. He argued that quantum statistics merely reflected human ignorance, not a fundamental feature of reality. His belief in a rational, causal universe was intrinsically linked to his profound Lutheran faith. He saw no conflict between science and religion, viewing them as mutually supplementary paths toward the divine order. Planck asserted that science, by uncovering the elegant laws of nature, arrived at God as the crown of the edifice. He believed these laws were discoveries of a pre-existing intelligent mind, the matrix of all matter. Max Planck died in Göttingen on October 4, 1947, at the age of 89. He had lived long enough to see his nation destroyed and his greatest scientific principle, determinism, overturned. His ultimate legacy lies in profound irony. His name is now synonymous with the Max Planck Society, a global leader in the quantum physics of uncertainty, the very world he resisted until his final breath. Planck's first great invention was the quantum itself, the concept of energy existing in discrete, granular packets, a foundational principle that shattered classical continuity and redefined physical reality. His second critical invention was the constant h, Planck's constant. This tiny fundamental number governs the scale of the quantum world and acts as the crucial bridge between the particle and wave natures of all matter. The most tragic of his lost inventions were his priceless scientific archives, his personal diaries, notebooks, and correspondence with the greatest minds of his era, all consumed by fire in the 1944 Allied bombing of his home. The scientific mystery Planck unlocked was the fundamental, discontinuous nature of reality at its smallest scales, a paradox that haunted him and still challenges modern physics. The secret code Planck discovered was the fundamental language of the universe. When the old classical code failed, his act of desperation yielded the key cipher, the constant h. In finding that constant, Max Planck became the first to read a line written in reality's true source code, forever quantifying the relationship between energy and frequency. Though he spent his later years unsettled by the strange alien grammar of the quantum message, his discovery gave humanity the revolutionary power to read the book of nature anew.